Hello everyone. Today we will continue to talk about the topic 2, instructions. We will continue with the section 2.7, instruction for making decisions. Again, like I always say, please read the corresponding material in your textbook in order to get better understanding about the material delivered in class. So before we talk about the content of today's class, let's recall what we have learned for the decision making. In last class, we said there's two different type of decision making: conditional decision making and unconditional decision making. For the conditional decision making, there is two different operations, the main operations or instructions. One is a branch if equal, and another is a branch if not equal. So the branch if equal, one example for the format is branch if equal followed by two source operand and then the label of the instructions. Branch if not equal has a very similar format with the branch if equal. Basically, what here mean is try to compare whether the source operand T1, D2 are equal. If they are equal, I will transfer my control into the instruction with label L. If they are not equal, I will continue to implement the instructions right after this branch if equal. If you recall, the secret of instruction stored in the instruction memory as a one-dimensional array. So basically, you after implement this, you will implement next or the ones with label L. Similarly, for branch if not equal, I still will compare the two source operand, T1 and T2, try to see whether they are equal. If they are not equal, I will transfer the control into the instruction with label L. Otherwise, I will continue to implement the instructions right after branch if not equal. For the unconditional decision making, until now we learned one instruction, which is jump. What does jump L mean? Please pause here, try to think by yourself to see whether yourself can answer that. Jump L means I try to jump or branch or transfer my control into the instruction with label L, and there is no condition to limit my this decision. Okay, and if you recall, near the end of our last class, we represent assembly language for a while loop. We mentioned this solution, this representation, is give a very straightforward representation or translation from the high-level language into the assembly language. However, this is not that efficient. One reason is we have a loop, we have a jump into the loop. In other words, no matter how many times you need to implement the loop, you need to implement exactly the same number of jumps. For example, if you want to implement 1,000 times of the loop, you will implement 1,000 times of jump. So in order to maximize or at least improve the performance of the implementation, whether it's any way, we can pull this or move this instruction outside the loop. By doing so, instead of implement the same number of loops, I will only implement the jump one time. By doing so, we reduce the overall number of instructions we need to implement in order to finish the while loop. And if we want to use time to evaluate the performance of the computer, in that way, that means we improve the performance of the implementation. So now let's try to see how we can do that. So first, we need to initialize the value. Basically, we need to get save I. We need to know how to get the save I from the memory to the register. So the first two lines is the same as the original one. Basically, I need to shift T1, shift S3 to the left by 2 bits and store that value to T1. I want you to pause here to ask yourself, what's this instruction trying to do? Please think that and then try to answer it by yourself and then continue with this video. So what I here try to do is, I try to calculate the offset of the memory address of save I compared with the base address of the array save. In other words, I try to calculate the offset of the memory address of save I compared with the memory address of save 0, which is the original base address of the array save. And after that, next step is we try to change or convert the original base address of save, which is memory address of save 0, into a new base address to enable us to implement load word to load the save I from memory into the register with a standard format. I think in last class I explained why we try to do so in many times. Hopefully it's clear. So in order to convert the base address from the memory address of save 0 to the memory address save I, the first thing is we need to calculate what is memory address of save I. Therefore, I try to calculate the summation between T1, which is offset of save I, with S6, which is the original base address of save. So in that way, this addition between these two will be the memory address of save I. And I'm using this value to update save at T1. Now T1 is the memory address of save I. Okay, so after that, I will directly do the test by using unconditional decision making. So basically, I don't care what happened, I will do the test. What test is? I try to test whether save I is equal to k. So yeah, to achieve this, the first I need to load the save I from the memory into the register T0. And because now we have the new base address, which is T1, which is the memory of save I, the offset for this representation of load word is just 0. So because of that, we are able to represent the load word still as the conventional format, basically constant outside of the parentheses. After that, now T0 has the save I, right? Just want to mention, right? The T0 is save I now, right? Let me just give you more representation. Here, what we just say is T1 is the offset of save I, right? And here, now the T1 is the memory address of save I, right? Okay, so now I jump. So I try to first this test, the overall test. I try to compare whether the save I is equal to k, right? So now I already T0 already has a save I. Next, I will just do the compare, right? So basically, I try to say if T0 is equal to k is in, let me say, k is in S5. So if equal to the register F5, then I will branch back to the loop. Otherwise, I will just outside of this whole procedure. So what this loop is, let me just use loop. Again, you know, the label doesn't matter, right? We said in last time, the ASCII value, because no matter what, the computer will not read ASCII number, right? So you're using loop. You're using L or using Jean. Whatever ASCII value you want to represent here will be fine.